Welcome back. Hope you had a good lunch. And now we're ready for the last two blocks, which will be the most advanced ones, but also the most exciting ones. So I hope you have energy left. It just happens, twice a year, so you got to really use your time well here. Anyway, we talked about multiple indicator growth over time, and that's an interesting topic that seems to be corresponding to a methodology that's very underutilized and could be developed much further with the help of substantive and methodological thinking, as we will see here. If you're on slide 98, you have what I have on the screen here. We're going to take a look at 4 different cases. We have different degrees of invariance in these different cases. In case 1, we started off with case 1. We had the same items across time. And we started off with the model of believing or hoping that all items would be invariant, in which case we certainly would be certain that we had the same construct measured at the different time points. And in the same metric as well, due to holding the item intercepts and slopes invariant. Now, we found, however, that we slipped from case 1 to case 2 by the fact that some items were non-invariant. And it turned out that they were invariant with respect to loadings, but not invariant with respect to all of the intercepts. And that seems to be the case quite often in factor analysis type of exercises. And it's interesting because historically invariance testing in factor analysis only concerned the loadings, not the intercepts. Now we have to bring in the intercepts in order to do growth modeling. So we can study change over time. And we find that it's harder to fulfill item invariance with respect to the intercept measurement parameters. But we found the majority of the items were invariant. And one could argue that we still have the same construct over time and in the same metric due to the fact that many of the item parameters were invariant. But at some point, it becomes useful to consider a case 3, which is a case of different items across time. And that's an approach that's very often used in educational testing, and actually is what the LSAE math achievement data were based on, where an individual who did well on a math test in grade 7 was given a harder test in grade 8 than those who did poorly in grade 7. So adaptive testing designs, trying to match the item difficulty with the person's ability to get better measurement precision of the ability. And that's an idea that can be used much more broadly in situations like TOCA. I'll return to that in a second. But the idea is that you have some items are the same across time. I think they're referred to as anchor item in educational testing and so-called item response theory. Item response theory. Oh, that's interesting. So you have to have some items the same, but some other items can be different across time. We'll take a look at that. And we have to have some item invariance across time to be able to study the same construct and therefore study change across time. And then ultimately you come to a case 4 where it is too difficult to force invariance across time. Because the item functioning is so different across time, or because you have to have different items measuring the different content across time. Some items may be invariant, but ultimately it falls apart and you will deal with different constructs. In fact, math achievement development across grades 7 through 12 could be said to be of that case 4, because you have a situation where the items change in nature across time. In 7th grade has a lot to do with numbers and operations, whereas then in grade 8 you start to sprinkle in algebra and geometry and calculus. So the math content changes nature from grade 7 to grade 12. certainly you can have the same items across adjacent grades to anchor down this invariance notion, but and have a score in the same metric. But the question is if the same construct really is measured. It's all math, but it's different kinds of math. And I think it's an open question whether or not that matters if the construct changes nature in a natural way over time. For instance, if you're going to compare males and females, well, it doesn't seem like it matters if the construct changes a little bit in nature, because it changes the same way for males and females. So take a look at this picture here and see what you can, what that tells you. This summarizes the story perfectly, right? So the idea here, there's an idea presented up at top left, sort of like a riddle. So the idea is one of starting off with 3 items, item A, B, C, finding out that item C at the second time point is no longer age appropriate, and we change from the C item to the D item, whereas we keep the A and the B item and can therefore assume measurement invariance across time 1 and 2 for items A and B. By having those 2 items invariant, we can hold the metric of the factor the same, and by the fact that we have a majority of the items, 2 of the 3 is just an illustration here, invariant, you can argue that we're measuring the same construct. But we are able to switch out one item, C, and make it into a D. And at the third time point, B becomes age irrelevant, and we put in item E instead, keeping item A and D from the previous time point, so we can have measurement invariance between time 2 and 3 for items A and D, and onwards and upwards at the 4th time point. So that's the idea of longitudinal development of scales used in item response theory. And you could do that also in a context like aggressive disruptive behavior, where an item like stubborn means something different in early grades than in later grades. So that's sort of a developmental psychometrics that's an area that needs to be developed further, I think, where you want to have items that are age appropriate. You shouldn't use an item for high ages that no longer has any relevance for those ages. And you should have items at certain ages that really can capture the relevant change that you're looking at. So this is case 3. This is case 3. And what about this? At the bottom of slide 99, well, here's a way to try to solve the age-old problem of you have a longitudinal study, and you have a measure that you used for ages over many repeated measures, but new research is showing that that scale, that measurement instrument is not very good. And you want to replace it with a new measurement instrument. But if you replace it with a new measurement instrument, you cannot study change because the measurement instrument changes. So what do? Well, you could have the old measurement instrument at time 1, and then at time 2 and 3, you could have both the old and the new measurement instrument. So you have multiple indicators, at least 2, where you could have invariance across time 2 and time 3. And then at time 4, you only use the new one. This model is actually identified under these invariance assumptions so that you have the same metric for the factor down here and can shift over from the A scale to the B scale. And actually, I showed this picture about 10 years ago, I think, and at least one person has now written a paper on this. And it's on our website under the papers section, under the heading of, I think it's under growth modeling, so you'll find it there. I think it's Margaret Keeley who did that. Any student of hers in the room? No. Yes, am I right? Yes. Do you know which journal that appeared in? Yeah, well, you have the paper on our website at least, so you can take a look at it. It's an interesting methods question too. Would it be sufficient to have only one time point with overlap of the old and the new measure? And how reliable is this to violations of assumptions? That could be studied. So this idea doesn't seem to be used at all outside of education, and I don't know why. So you can have measurement instruments like the TOCA as one example, the aggressive disruptive behavior, where the items change in a planned fashion. The statistical methodology is there to deal with those kinds of data. People should just construct their instruments to capture development correctly in that way. Now let's go to embedded growth models. And we are down towards the bottom here. We are at the bottom because the last bullet corresponds to August content. So let's take a look at this model that we had before. It was it's actually a conventional multi-level model, two-level model in hierarchical linear modeling terms. Measures repeated over time and measures taken over several individuals. And we have the time-varying covariates here, and we have a special feature of a random slope STVC, slope for a time-varying covariate, that tells us how much math course taking influences the math performance for different individuals. So that's a standard model in the multi-level world, but let's spice it up a little bit. So you see what we did there? Now we're doing, well, you didn't see it? Yeah. We're saying that we let I predict the growth rate and let I predict the slope for the time-varying covariate. So we are now using this idea of initial status influencing what happens later. So this is no longer a standard multi-level model. This is a different animal. What about that? So far here, I, S, and STVC are they're latent variables, but they're latent variables of the random effect kind. Now let's bring in the old-fashioned psychometric kind of latent variable, F as in factor, which is a background variable, grade 7 parent and peer academic push, a measurement instrument talking about the encouragement to academic studies from parents and peer, a measurement instrument that is given to the student. So we have a factor that influences the growth factors, the random effects, and that factor is in turn influenced by background variables, the time invariant covariates. So there is an idea of a factor that is predicting the growth factors and it itself predicted by background covariates. So there's a non-standard multi-level model. And it is an example of what I call an embedded growth model. The growth model is only part of the whole picture that you're interested in. And what about this? What do we do here? Well, what are we doing here? What substantive question, which substantive question are we answering here? Well, we're answering the question about, we're trying to answer the question, why do males seem to overtake females in math performance according to the plot that we showed yesterday morning? And one possible explanation could be that males are encouraged to take more advanced math courses. Let's postulate that that is the hypothesis. Well, so then we should look at female, the variable female influences math course taking. So the math course taking is no longer a covariate, it is a dependent variable. You predict the amount of math course taking from a variable such as gender. Right? So now suddenly the background variable becomes a foreground variable, which then in turn influences the math performance. But we're not really interested in the marginal effect of gender on math course taking. We're more sophisticated than that. We're going to try to figure out, given two students with the same initial status on math in grade 7, given two students with the same I value, do females tend to take fewer courses than males? So it's the partial effect of gender given the value of the initial status. So you have two equally bright students. Is it the case that females tend to, that the female tend to take the math courses to a lesser degree than males? So there's the question posed in the path diagram. I influences math course taking. See those arrows? And female influences math course taking. So we want to know if the female partial effect is significant or not. That would answer an interesting question, perhaps. And then at the same time, what goes on is the F measurement model and the I influencing S, I influencing STVC, and STVC still being the random effect here. So now the flow of influence comes from time invariant covariates and F to I, and I goes to STVC, and I goes directly to the time varying covariates down here, which then go back up to math. So I plays a very central role. It has a direct effect onto math, but it has an indirect effect to math this way, down and up. It's actually doable. I did this analysis, and I live to tell about it. It's not hard. No. Huh? Now, what did I do here? Well, here we get used for our developmental epi language. We're introducing a distal variable, dropout of high school. Here we have the proximal. In this case, it's math. There's no intervention, but we have the distal dropout. It's a binary dropout variable. So we're going to entertain a logistic regression here, where dropout, what should it be influenced by? It should certainly be influenced by time invariant covariates. But we could also say that it should be influenced by the initial status of math, and could be influenced by the growth rate of math as well. If you have low initial status and low growth rate, the student might become discouraged and disengaged from school, math being a challenging topic, engaging the school engagement, and therefore those I and S could influence dropout. So you could do that analysis in maximum likelihood. So that gets closer to the substantive researchers thinking about these phenomena, right? It's more elaborate, more complex, but it is closer to how an educational researcher might want to think about high school dropping out. So this is what I call an embedded model. It's elaborated in different parts, and the growth model is only one part of the model. And of course, this is a complex model, and if you want to try to analyze according to this model, you wouldn't start here. You would be hopelessly lost. Something doesn't fit well. Well, where does it not fit? You want to take Linda's advice and go stepwise. First, do a factor analysis here to see if there is a meaningful single factor, for instance, behind here. You also want to do the growth modeling, first without covariates, then with covariates, then with time-varying covariates with random slopes, and then start building the model piecewise. You may want to do the dropout analysis based only on the time-invariant covariates, and perhaps Math 7 as a covariate, or Math 7 as a covariate, and Math 10 minus Math 7 to study gain. You know, it's just simple ways to get a feeling for what influences dropout. before you do anything as complicated as this. Two linked processes, just an example of another type of embedded model. Here we're back to head circumference of the baby at 0 months, 8 months, 18 months, and 36 months, and growth factors for that. And we predicted that with gender and ethnicity, but also mothers drinking during pregnancy. It turns out that in the data, we actually have a whole series of drinking measures during pregnancy, just before and different time points during pregnancy. So you actually could create a growth model for the covariate. Growth model for the covariate. And predict, use as a predictor of head circumference a point of the growth model. Say that this time point is biologically particularly critical. Let's let this be the predictor. And what is this? Well, this is, the way it's drawn, this is the systematic part of the variation in the outcomes that Linda has talked about. That is, it is the the position on the growth curve minus the residuals. So it's, if you look at it here at top right, it's I plus S times T. So it is a systematic part of the growth. And you can let that be a predictor. So that's fairly advanced linked process model. So let's switch away from that topic of embedded growth models and instead talk about power estimation in the context of growth models. And there's a lot of writing in the literature on power. In our psych methods paper, we talked about a method used in SEM, Satora-Saris approach, which you have a couple of pages on in this handout, and I'm not going to go through it at all. I'm just going to point at certain steps. That's one approach that you could use for growth models as well. And another approach is Monte Carlo studies that we talked about, and there's a paper that we refer to, which Linda's going to give you an example of in a second. Various kinds of websites have power calculations for growth models. Multi-level power writing is found in these references, for instance. And when it comes to multi-level studies within schools, there's further writing here. And one can also consider the topic in the cohort situation, etc. Many different contributions to this topic. So just to remind you what power is, in case you forgot the early training, you have a chi-square distribution here for testing, and you have a critical value here, and the probability of getting a chi-square value above that critical value is 0.05 when the hypothesis is correct, when the model is correct. That's a type 1 error. Type 1 error should be fairly small when the model is correct. But if the model is incorrect, as the bottom picture shows, then the probability is much higher, hopefully, to reject the model. This is the rejection. The shaded area is the rejection of the model. Probability of rejecting the model when it's incorrect is the power. So you want this part to be big. And in this case, when the H0 is incorrect, you can make a type 2 error, which is not rejecting the model when it's incorrect. So in typical cases, you want the shaded area to be large, say 80% of the plot of the distribution, whereas the type 2 error is fairly small. So the Satora-Saris method is very simple and easy to do in a program like Mplus. When you do power studies, you have to hypothesize what the parameter values might be for your studies. So hypothesize what the effect size would be in an intervention study, for instance. you create then a mean and covariance matrix for hypothesized parameter values. This is within a SEM framework now, so it has to be a growth model that's limited to what SEM can do. And then you analyze this, just as a check, you analyze this population covariance matrix that you've generated as if it was sample data, just to check that you get back the parameter values that created it. It's just a check. Then you analyze it again, but now misspecifying the model by fixing, say, a treatment effect in an intervention study at 0, whereas in reality, step 1 created the treatment effect to be greater than 0. And then you use the printed chi-square as an appropriate approximate, I think you should say, approximate non-centrality parameter for which you can compute power. This is the approach that's described in Multilevel and Curran, and it was used for the plots that were used in that paper. So you have the different steps illustrated here on these slides, and I'm not going to go through them. But those steps were used to create these beautiful power curves where you can see on the x-axis different sample sizes and on the y-axis power. So usually we want power at least 0.8. So you can see which sample size you need, about 300 for this case and a little bit more for the other cases. And you can see in the next plot how sample sizes, or how power for a given sample size, I should point here perhaps, varies as a function of how many time points you use in your study. So this could be used to argue for having to get funded for a certain number of time points. All of this is in the Monte and Curran paper. And here, what sample size do you require to detect an effect size, treatment effect size of different magnitude? So this is ES effect size from a small to medium to a high. And of course, you don't need as large of a sample if the effect size is larger. It's easier to detect. Now, here is a different take on power through a Monte Carlo simulation of data from a model. And I think this is Linda's turn.
Right. Thank you. Okay, so we're going to talk about a paper that Bengt and I wrote in 2002, how to use the Monte Carlo study to decide on sample size and to determine power. And this paper came about because we'd been teaching for several years at that point, and one of the most prevalent questions we would get was, how big does my sample have to be? And which is a very legitimate question to ask, but doesn't have a very simple answer, because the sample size can depend on the type of model you're estimating, the scale of your dependent variables, how reliable the observed variables are, and many, many other factors. So what we would say to people is, you really need to do a Monte Carlo study that uses as population values from your own study. And so obviously, where are you going to get the population values? Well, if you have nothing else, you can do an analysis of your own data, and you can use those final results as population values in a Monte Carlo study. So that's what we did, and then you can vary settings in the Monte Carlo study to see whether or not whether your sample size was large enough to be able to detect a difference if it was there to be detected. So if you needed, for example, as the Monte Carlo study said, you need no less than 500 observations, and you have 100, and you were not able to find the treatment effect you were looking for, then you didn't have the power at n equals 100 to detect that difference. You would have needed 500. So that's the logic behind doing this. It's to see in your very situation with data just like your data, what is it going to take to detect the difference you're looking for. So this paper is on our website, and you can take a look at it. So then I'm going to be talking now a little bit about how to do a Monte Carlo study in Mplus. Mplus has very extensive Monte Carlo simulation capabilities. And so, we truly recommend doing this if you're really interested. Like if you're writing a grant and you really want to get a feeling for how many observations you need, how many people you should sample, then this is a good way to start. In the user's guide, those of you who use Mplus know we have about 125 examples. And although they're based on simulated data, and this simulated data came about by us doing a Monte Carlo study for each of those examples to generate the data. So if you want to do a Monte Carlo study, then you should look in the user's guide, find the example that's closest to the example to your own analysis. Let's say it's a mimic model, or maybe it's a growth model. So find that, and then on the CD that comes with Mplus are Monte Carlo counterparts for each of the real data examples. And that's a good starting place. Then you can see how we set it up and what you need to do. So basically, we have a Monte Carlo. Well, let me put this over here because I think people see better. Okay, so the simulation study we're doing here is going to be for a linear growth model for a continuous outcome with missing data where attrition is predicted by time invariant covariates. So the missing data is MAR. So first of all, the Monte Carlo command exists in Mplus, and that's what you use to do a Monte Carlo study. There's several options. The names option gives names to the variables that you're going to be generating. So we're going to be generating 4 continuous y variables and 2 covariates. And all the variables are generated as continuous, unless we have the categorical option. But here we're all continuous. Then we tell for each data set that is created how many observations we want. So we're going to generate data sets of randomly sampled 500 observations from the population that we describe in the model population command. And when one does a Monte Carlo study, you do many replications. So you sample from the population repeatedly, and then you look at average parameter estimates over the replication. So we're doing 500. You need to give a seed. Well, you don't really need to give a seed, but you can using this option, seed. And the cut point option is used for covariates only. So all the covariates would be continuous unless you use the cut points option to cut them. And the value in parentheses is the z value where you want the cut to occur. So here I think this is something like an 84-16 split with a z value of 1. The missing option is used to indicate for which variables you're going to have missing data. So we're going to have missing data on y1 through y4. And as we said, the attrition is going to be predicted by the time invariant covariates. So we're going to have missing data, attrition over time. And we're going to be able to model that in this simulation study. So you can model the type of missing data you see in your sample data to get an idea of how that could affect power. So we'll just leave this up over here. So that's the model population command, or rather the Monte Carlo command. Now, in addition to the Monte Carlo command, where you give the basics of the Monte Carlo study, you have to give population values for every parameter in the model. And that's done using the model population command. And so we'll look at that first. And then model missing is used to describe the missing data patterns that you want the data generated with. So in model and just an aside, I mentioned, I think yesterday, that we have this new option in Mplus where all of the input statements can be provided to you with starting values that are the ending values of your analysis. That'd be a perfect way to get model population now. So you would run an analysis, your analysis on your own data, the one that you want to know whether your sample size is large enough to have the power to detect the differences you're looking at for, rather. So if you do that, and the new option is going to be called S values in the output command. If you put S values in the output command, then you're going to get statements like these that they're going to all have asterisk, but that doesn't matter. In model population, at and asterisk are treated in the same way. And then you can just use those for your model population. So anyway, in model population, you see that we have x1 and x2. And as I said, in model population, at does not mean fixed at, and asterisk does not mean free. They're indistinguishable. All they mean is we're going to give a population value after them. So for x1 and x2, we're saying the variance is 1 for those two variables, and the bracket statement says their means are 0. We give the growth model. We say that what the time scores are. We give the means of the intercept and slope growth factors. The intercept growth factor is going to have a mean of 1. The slope growth factor a mean of 2. And the variance of I is, or rather the residual variance of I, because this is a conditional model, is going to have a starting value of 1. Residual variance of S 0.2, residual covariance of I with S 0.1. And the residual variances of the outcome variables are going to have population parameter values of 0.5. And I won't keep going through this, but anyway, if you do not give a population parameter value for each parameter, they will get a population value of 0. So it's very important that you give something for every single parameter in your model, unless you want it to be 0, and then you can leave it out. So for model missing, let me move this, put that there. For model missing, this describes the missing data, or how the missing data looks. In model missing, each y is a variable that is 1 for missing and 0 for not missing. So this describes this describes for these missing value indicators their intercepts. And that's -1, and I think that comes to being, that's a logit. These are logistic regressions that we're describing in here, and they have nothing to do with the model to be estimated. They have to do with data generation. So model population and model missing have to do with data generation. Model population tells you the model population parameter values. Model missing tells you how the missing data look. And it tells you that by using 4 binary missing value indicators where 1 is missing and 0 is not, and setting up logistic regressions and giving the intercepts. Now the intercept value, if you only had this in the bracket, then you would be only generating data missing completely at random. And I think the percentage is like, we're saying 23% randomly missing data over all of the time points. So the same amount for each variable. But now in the on statements where we relate these missing value indicators to the covariates, what we're saying is that missingness is related to the covariates. So that is no longer MCAR, it's MAR. So then all the data generated will be MAR. And as you can see by the logit values that have been chosen, that at time 1, we have 0.4, time 2, 0.8, time 3, 1.6, time 4, 3.2 for x1, the continuous covariate. And for the categorical covariate, it's 0.2, 0.4, 0.8, 1.6. So what this is saying is that missing data attrition over time is occurring. So as over the course of the development, people are dropping out. So there's this continuous attrition. So the model population taken in conjunction with model missing describes how the data are going to look that are generated, both in terms of population parameter values and missing data. Okay, and then we have to give a model to be estimated. And that's given in the model command. So as each data set that's generated is analyzed according to the model in the model command. And in the model command, you do not want to mention these statements about the x's in the model population command, because the model is estimated on the x's, and their means, variances, and covariances should not be part of the model command. And so here in the model command, it matters whether you say @ for fixed or asterisk for free. And you give values also in the model command, you'll see. And in the model command, the values you give have two purposes. One is for the model coverage, or for the coverage of the parameters, to see that's the value that we compare how well estimated the parameters are. So we don't take the model population values. Those are used only for data generation. So for coverage, you get the value from the model command, also used as starting values. Okay. Oh yeah, one other thing. Output command. If you ask for Tech 9, then for each replication, if there's a convergence problem or any other type of a problem, you'll get the error message in Tech 9. So Tech 9 can be very useful. If when you complete your analysis, it tells you how many, we asked for 500 replications, and it will tell you how many requested, how many completed. So if you had requested 500 and only 450 were completed, if you look in Tech 9, you'll see the reasons that the 50 weren't complete. Okay, so we have one thing here to look at. So in the model results, we have a new columns to look at here. So we have here population. So these, and this is a little confusing because we say population, but these values aren't taken from model population. They're the population coverage values taken from the model command. So these are what we would want to be able to recover by our Monte Carlo simulation study. Under average here, we have the average parameter estimates. So we ran the analysis 500 times. We get 500 I on x1 values, and this is the average. And you can see it's very close, 1.0032. And I on x2, this parameter is also recovered very well. And it looks to be the case for all of them. They're very close to the population values. Now, if we either increase sample size or the number of replications, we could get closer. So you can see, so then, like if you weren't satisfied, if you didn't think this was enough, then you could increase your sample size to 1,000 and see if that helps you. So at a minimum, you want to be coming close to the population value with your average estimates. Then we give the standard deviation. And that's actually over the 500 replications. We take the 500 parameter values and we compute a standard deviation. what is an SE average? That means that from each replication, we take the standard error for the parameter estimate and we average it. So there's two ways of looking here. Then we see this column 95% coverage tells us we want the coverage value to be 95, and it tells us how close we are. We have 0.936, 0.952, et cetera. If we want to increase the coverage, we could increase sample size or number of replications possibly. Now the column that we're interested in, so as far as power goes, is the last column. And when you do this type of analysis for sample size and power, it's really power for one parameter. So you have to decide, like if you're doing a treatment control, you would be interested in the treatment effect. That's what you want to detect in your study, treatment effect. So you want to know the power for that. So let's say this S on X2 is treatment effect. If you look in the power column, you'll see that it's 0.83. And as we know from studying power, anything greater than 0.80 is usually deemed to be good. And what that is over the 500 replications, it's the proportion of the z-tests that were significant. So the proportion of the z-tests that were significant that concluded that this parameter estimate was different from 0, that number constitutes power. So we have a power of 0.83 to detect that 0.2469 is different from 0. So that's just a basic overview on how you would use our Monte Carlo simulation facilities to be able to determine sample size and estimate power. Oh, he fell asleep. Too bad. Wake up. It's your turn.
You ready? That is so soothing. Tell me another power story. So let's see what comes next. Well, here are some considerations related to power for cohort sequential designs. But I'll leave that slide for you. And instead, we're going to switch gears, folks. We're going to talk about survival analysis. Wow. That should wake you up. Okay, there are two kinds of survival analysis. One that's easy to understand and one that's very hard to understand. So I deem the discrete time survival to be easy to understand and the continuous time to be hard to understand, but others may disagree. Certainly the readings on this, it seems like the discrete time survival is a little easier to understand. So I'm going to start there. And this is a topic that you could spend, like all of these topics we talk about, you could spend a week on if you wanted to cover it thoroughly. So we're going to give you further readings on these. And what I'm going to try to do is just an introduction of the topic for you to have an easier time to make further studies. It's another type of analysis that I think is underutilized among social and behavioral scientists, particularly now when it's relatively easy to do this kind of analysis. The discrete time survival analysis considers infrequent measurements and limited number of time periods, continuous time frequent measurement and large number of time points. But both of them share the idea that we're trying to build a model for the time it takes for a certain event to happen as a function of certain predictor variables. So time to event. And there are many research questions that are related to that. We talked about time to onset. In education, they have studies of time that it takes for a teacher to quit her job. Happens a lot in education. And survival obviously has to do with poor outcomes, including death or reoccurrence of a medical problem. Discrete time survival, you have quite a lot of good writings on it, as I said. You have terms like event history analysis. Good references include Paul Allison's. And Singer and Willett is a book that I warmly, actually that's a paper that I warmly recommend. We'll get to the book later on. And Jerome Vermunt in Tilburg, Netherlands, has written about this quite well also in his dissertation. So the first setting we're going to consider is discrete time periods, for instance, grades, like we saw in the TOCA data. And we're going to consider a non-repeatable event, an event that can only happen once. Onset of drug use, for instance. The aim is to estimate survival curves and hazard probabilities and relating survival to covariates. And there are many more complex versions of this model with multiple latent classes of survival. That is mixture models in survival setting and survival modeling with continuous latent variables that we're not going to directly talk about today. We're going to take a look at an application that appeared in Monte and Mason's paper in the Journal of Educational and Behavioral Statistics. It has to do with Hopkins data again and school removal, the first time a child gets removed from school, and how it relates to aggressive behavior in the classroom. So we're going to define a U variable, event history indicator, and it is binary. So we're going to think of it as a categorical. And where U is equal to 1 if individual I experiences the event at time period J. And I'm going to go straight from that slide. Actually, consider this slide in more detail as an example. So say that you have 1, 2, 3, 4, 5 time periods. That could be 5 different grades. We're going to talk about censoring in the sense of losing information. An individual is censored after time period 5 if that individual did not experience the event. If the individual wasn't removed from school during those 5 time periods, then the individual will have its U vector scored as 0 throughout. So U1 is 0, U2 is 0, U3, 4, 5, 0. An individual who experiences the event in period 4 would have 0 for U1, 0 for U2, 0 for U3, 1 for U4, and then missing, which we denote by 999, thereafter, for all the time periods thereafter. An individual who drops out after time period 3 is censored during time period 4 before the study ends. So the person drops out of the study, then you get 0, 0, 0, and missing. If you do this kind of scoring of a U variable, you will get a discrete time survival analysis as defined by these authors, but you will have it now in a framework which is more natural to the modeling that we've been talking about. So you could draw a model diagram like this, where these are the event history indicators scored as 0, 1, or missing. And you can relate the hazard, the probability of the event, to an X variable in this fashion through a logistic regression. There are other ways to deal with the data, to set up the data, so that discrete time survival analysis can be done. Actually, can be done by logistic regression. But that is manipulating the data in a different way that's perhaps less natural to the longitudinal wide data format that we've been talking about. Now, from these models, for these models, you define the probability that the event occurs at time period J. as a hazard, which, as you recognize, is 1 over 1 plus e to the power of something. This is the logistic regression model. The logistic regression model, where you have a linear logit sitting in parentheses, linear logit, with a slope kappa multiplying x and an intercept which we refer to as a threshold for a categorical item. And thresholds are negative intercepts, so we change the sign here. But this is a logistic regression from the probability of experiencing the event in time period j. It's expressed a little bit more in detail. It says experiencing the event at time period j if you have not experienced the event earlier. So I'm going to give you an example of that. And here we get a so-called proportional odds assumption excuse me, embedded in the model if we drop the j subscript for k. That is, dropping the j subscript would mean that x influences u the same way at all time points. So that would be, if you look at the right screen, it would be saying that u1 on x, its slope is the same as u2 on x, u3 on x, u4 on x. So you can say, you can use the equality approach in Mplus to say that those slopes are equal. That would be a proportional odds assumption. But the more general model has a subscript j, which is so this is a non-proportional odds model using survival terms. So that has to do with the hazard function, the hazard of experiencing something, the probability of experiencing something. And the survival function can then be derived from these hazards h as this product over time periods. If you look at, here's the likelihood. If you want to look at that, it's from the Jeb's paper, but we're not going to take time with that. Instead, let's take a look at this example, which will make this idea clear. And this is from the Hopkins data, where we have, if you look at this panel, we have males at the top, 200 males, and 203 females. And we have the different grades, 1 through 7, as the rows. And then we're going to focus on the column here of school removals. So in grade 1, we have 4 school removals. So we start out with 200 children, and 4 out of the 200 experience a school removal, which means that we have a 2% sample hazard. So the hazard is 2%. Among the surviving 196, the surviving 196, 200 minus 4, that have not yet experienced their first school removal, among those 196, 5 experience school removal in grade 2. So the 196 is considered the risk set, which is a different set of individuals than in the beginning of grade 1. So 5 under 196 is then the sample hazard. So this is what we tried to convey with this expression. Those who survived grade 1, not being removed for the first time in grade 1, what's their hazard of being removed in the next grade? 2. Then when you come to the 3rd grade, you have to subtract 9 people, 4 plus 5, from 200. And that would be 191 in the risk set, out of which 7 experienced their first school removal. The hazard is 0.04, and onwards and upwards. And actually, I think there is a typo here, which I found out lately, and should be 100 and... I think I wrote it down there. What does it say?
Oh, yeah, you did, 150.
It should be 150 here instead of 136, I think. So the hazard is probably wrong as well, if you figure that. So you can do the same thing for females, and you see that females have a lower hazard throughout. But for both males and female, the hazard seems to increase over grades. So kids get a little bit more rambunctious as they get older. These things can be plotted now. You can take these sample hazards on the y-axis and plot against the grades, and you get different hazards here that you can, hazard profiles that you can take a look at. Actually, here we did it by looking at males and females, and looking at below and above the mean for TOCA 1F, which means the aggressive disruptive measurement score in the fall of first grade. So we have, this looks like the males. These are the males. Boys are bad, girls are good. Males above the mean, males who are particularly aggressive disruptive in the fall of first grade, they have the highest hazard of being removed from school, whereas females below the 1 standard deviation below the mean on aggressive disruptive in fall of first grade has the lowest hazard. New feature in Mplus version 6 is that these hazard functions can be plotted directly in Mplus. And not only that, but the survival curves can also be plotted. So here it's a survival which says what the probability is to not be removed from, to survive means to not be removed. So you have the corresponding survival, and again, the worst survival curve is the lowest curve here. You have the lowest probability of surviving, lowest probability of avoiding being thrown out of school is for males that are 1 standard deviation above the mean of the aggression score in the fall of first grade. So there are ways to scrutinize your data that way. And you can also obtain these types of plots for the estimated model. This is the sample quantity, and then you also get it for the estimated model. Here are different kinds of survival models that you can entertain, just an overview, and Linda will then give you an example. So now we draw our model figures more and more crudely here as the day goes on. Here's a rectangle for U, which implies that we have several U's, U1, 2, 3, 4, 5, right? Or we just draw it drawn out, which means a longitudinal series of event history. And we have a set of X variables that influence U. That's the standard survival model. And the way it's drawn, and we don't indicate any equality here, so it would be actually then be, if there's no equality, it would be a non-proportional hazard model. On the right, you have a proportional hazard model. And how do you see that? Well, you have a factor F that's measured by U with factor loadings 1 throughout. So these are several U's, not just 2, but several. And that factor F is regressed on X, which means that U1 relates to X as 1 times beta, second U 1 times beta, up to the last U 1 times beta. So this imposes the equality restriction by the trick of a factor here. So this model and that model will be the same if you have equality here. Then I will show you an example. The reason this F is introduced is because when you have a residual here, you have a so-called frailty hazard model, a little bit harder to estimate. And then I will go talk a little bit about that. Bottom left, you have a hazard survival model combined with the latent class model that we're going to talk about in August. Different latent classes of individuals having different hazards. And bottom right, you have a combination of, can you see what this model says? Well, here is very much shorthand for a growth model. A rectangle of Y's and maybe an ellipse for eta, so these are growth factors. And actually you have a growth mixture model here, which we're going to talk about in August, influencing the hazard or influencing the survival model part. And with that, I think it's time for Linda to jump in.
The hazard goes up.
No, I'm just asking, isn't that what that is?
Yes, the
Right, we
middle
know-
scale.
Exactly. Okay. Actually, I'm going to go put 142 over there. Thanks. So I think we're going to want to refer back to that. And then here we want to have 143. Okay. So let's take a look at how we would set this up in Mplus and to estimate a discrete time survival model. You can see here we have U1 through U7. These are the event indicators, and this is the event is school removal. So we have 7 event indicators, and we have several covariates. Race, lunch, CAV TOCA, which is the average class TOCA score. CAV lunch is the average class lunch variable, which is related to poverty. And Y1, which is the student. And I'm not sure what the other one is. Control group. Okay. So and then control group is this one. So missing are, everybody has 999, and we have to define the event indicators as categorical. So we use the categorical list. Now, in the model command, you can look at the model that Bank showed here on the right-hand side of the left screen. And we can just go straight from the model diagram to the model command. So we have F by U1-U7 at 1. So thinking that there's 7 U's here. And then we regress F on the covariates race through gender. And then we say F at 0. So we don't estimate the residuals like we show in the model diagram. Remember, Banks said this is a proportional hazard model with frailty. This is just a proportional hazard model. So this is the basic proportional hazard model, and it depends on one thing, input statement that we don't have that it's really important that everybody writes down. So please add to your input statement here, in the analysis command, estimator equals MLR. Right. Analysis. Which isn't there, right? So it's analysis : estimator equals MLR. Add that somewhere here. It doesn't care. It can be under output or wherever. It doesn't matter. But just add that, because the reason is because if you don't use maximum likelihood to estimate the model, it's not going to be a discrete time survival model, because the regressions are not going to be logistic regressions. It will default to the weighted least squares estimator. So it's very important, and in the user's guide, this is specified correctly. We just, somehow we dropped estimator equals MLR. Well, gee, okay. But anyway, so the reason this is a discrete time survival model also is because of the way the data are set up. So you must set your data up like Banks showed. If a person never experiences the event, they get all zeros. When they do experience the event, they get a 1, and after that, always missing. Excuse me. If they drop out of the study, they get 999. So they would only have zeros and 999s. Okay, so for this, let me have a drink of water. Sorry. So for this actually to be estimated as a proportional discrete time survival model, you must use maximum likelihood estimation, and the data have to be set up according to a specific pattern. Now, let's talk about what you could do over here. You could actually estimate the frailty by removing f at 0. And then you would have a proportional hazards model, but with a frailty being estimated. And the frailty is like a residual variance. So if it's significant, it would indicate that somehow more covariates that could have been included in that model. So that's one alteration that we could make to this model. The other thing we could do is estimate a non-proportional hazards model. And how would we do that? Well, then we wouldn't be using the F by construction that Banks shows. We would just be doing U1 through U7 on all of the covariates. There would be no equalities or anything. So you just basically remove the equalities and go straight from the U's to the covariates. U on the covariates, no equalities. So, and that would be a non-proportional hazards model. Okay, so, but now we're going to be looking at the results for the proportional hazards model without a frailty. So if we go to the next slide, whoops, let's not, we have our regular fit. That's not too interesting. So go to slide 145, and you'll see that we get thresholds, and these are actually the estimated hazards in a logit form. The logits can be turned into probabilities, and that talks, so as the thresholds decrease, the probability of school removal increases. So school removal is going to increase going from time 1, earlier grades, I think grade 1 to grade 3 or something in the spring. So school removal probability increases. We learned that from the thresholds, which are hazards in logit scale. And then when we regress F on this, it's really the regression of all of the U's on race, lunch, whatever, with the equalities. So F on race is like U1-U7 on race, where all of the regression coefficients are held equal across race. And so let's see what we see about school removal. We can see that the largest Z value is for Y1, and Y1 is the individual's TOCA score, so their aggressive behavior. And we can see the positive relationship. So as that increases, it's likely that a student will be removed from school. What's sort of interesting is the CAV TOCA. That's the average TOCA score for a classroom. So a classroom with a lot of really aggressive, disruptive kids would have a higher score than a classroom with really well-behaved kids. And you can see that there's a negative relationship here. And, you know, this is not my interpretation. It's Banks, so I'll give you credit. Right. What a wife. Okay. So anyway, his interpretation, which I think is pretty good, is that if you're in a really aggressive class, it's going to take more to get removed from that class than if you're in a class with really well-behaved kids. Just the slightest infraction, you know, can get you thrown out of that classroom, whereas you have to be pretty bad in the other to even get noticed.
You know, I don't buy that.
I'll shine this on you. No, anyway. But anyway, so this is the basic flavor of this, and how you would actually do discrete time survival analysis in Mplus. When we discovered that we could do this several years ago, we were really excited. And we still are. Okay, it's Banks' turn again.
All right, we're on the home stretch, folks.
And we're going to slide 154.
154.
Oh, wait, it's time for questions. I didn't notice, it's already 10 to 3.
Can we just wrap this up?
You want to do the whole rest of survival analysis?
It's not long.
Okay. I'll believe you.
Before you get your coffee break, let me just do this to set us up in a good way for talking missing data, which is an important topic. Now we're switching to continuous time survival. And in continuous time survival, you tend to see similar curves, survival curves and hazard curves. You also see something called Kaplan-Meier curves. And here's a Kaplan-Meier curve from a real data set. And Kaplan-Meier curve is a sample, it's sort of like sample statistics. It is not model-based. So this discusses survival curves in a randomized trial, treatment and control. And one can see how the treatment and control groups differ in their survival tendency. So this is something you can now ask Mplus version 6 to do to study your data and understand it in the continuous case. And one can contrast then the sample statistics survival curves with estimated survival curves for what's called the Cox proportional hazard model, proportional hazard corresponding to the proportional hazard model that Linda talked about, except where you have a continuous outcome. And you could immediately visually see that there is a difference between these two curves, right? The fitted curves don't look like the observed curves. The fitted curves are characterized by being separated from each other, pretty much the same, whereas the observed curves actually cross each other here. So you can tell then that a Cox proportional hazard model would not be suitable for these data. These few survival slides, continuous time survival slides, are from a final report that the Mplus team did in collaboration with the researchers at Eli Lilly, Mark Boy and Michelle Hackshaw and April Negley, some of whom are here at Lilly, worked together with the Mplus team to do a very interesting survival analysis of a cancer trial, where the interesting extra feature is not only this proportional, non-proportional hazard idea, but also the notion that you want to study not only survival time that is extended by a certain drug. This had to do with mesothelioma, which is a very serious cancer of the lung, with short survival time, but also weigh the extended survival time against the patient's self-reported well-being, the quality of life or patient-reported outcomes, where you do a combined analysis of survival and the growth model for the quality of life development. So that builds on and that report, I should say, that report with all of its Mplus setups using version 6 will be posted on our website with Lilly's permission, when version 6 comes out. So there will be a special survival section with all these inputs and all these plots being done. So you can follow that. It's an analysis that goes through very thorough latent variable modeling, as well as part of the pre-analysis leading up to a quite complex and intricate and interesting joint growth and survival model. So very briefly, what you model here in this continuous time survival is still time to event. But you formulate the model a little bit differently with the help of not only the survival time variable, but also a censoring indicator, C, where your patient is censored if survival, or death rather, happens after you have left the study. So here you're censored, here you're not. This is a model that can be, once again, expressed as a proportional hazard model, specifying that the hazard function is proportional to the baseline hazard function where baseline here can be considered to be the intercept of a model where the slopes are in this part. So if you take the logarithm of this, log of the hazard, the log of a product of the lambda term and the x term, log of a product is the sum of those two terms. So the log of lambda here will be the intercept. Log of x will be beta times x. So that is the slope part. So again, we have a choice between, well, within the proportional hazard model, you have a non-parametric shape for that baseline hazard and a parametric shape for that baseline hazard. We're not going to go into those two, that distinction, but just to say that the standard approach is the non-parametric hazard in the so-called Cox regression. Here is how simply you do it in Mplus. You define a survival variable t, and you define a time-censored variable, censored or if the individual is censored or not, that is, have you seen the death or not? And you can choose between the two baseline hazard variations. I think base hazard off is the default at this point. And then you have the survival is simply t on x. T on x. X will tell you how the hazard of death is influenced. So you get a certain coefficient here. Very simple. Very simple to do. Here is a slide about the data. I'm not going to go through that. There's two slides about translating continuous time survival to discrete time survival data. I'm not going to go through that in the interest of time. I'm just going to show you another plot here before you get your afternoon snack. And that is a cumulative, log cumulative hazard is a very useful feature. I'm going to point you to a very readable book by Singer and Willett describing these in details. But the log cumulative hazard is another sample statistic that you can ask Mplus to plot like this. This plot comes out of Mplus version 6. And you can contrast that against the log cumulative hazard curves for a non-proportional hazard model linear in time. So here you have then a non-proportional hazard. And you see that in this case, these two curves seem to be agreeing quite well. So the non-proportional hazard model seems to fit the data quite well, and therefore would be chosen over the proportional hazard model. I'm just going to scroll back to this figure here. The proportional hazard model, you can see that it doesn't fit the data already in the survival curves. You could have done the log cumulative hazard for that as well, but it certainly does the non-proportional hazard. The non-proportional hazard model certainly seems to fit in terms of the sample log cumulative hazard, and it would have also fit in terms of the survival curves. So these are just illustrations of some new plots that you get to do your survival modeling easy in Mplus. Finally, here's the way that non-proportional hazard modeling is done in Mplus. Very quickly, we had the time period that was considered in this clinical trial was divided up into a number of time segments. I've illustrated with 10 time segments here, where X, in this case, the drug, compared to a placebo, is allowed to influence survival differently across time. So that's a non-proportionality. You split up the survival variable into 10 parts here, and you allow treatment, the X variable, to have different influence on those different parts. Here is one of the final models we considered, growth and non-proportional hazard modeling. So the survival model here is augmented with a growth model for Y, where the Y's are the patient-reported outcomes, so-called quality of life outcome, the quality of life score that the individual has. And we want to see the interplay between the quality of life and survival. is it perhaps the case that when the slope of quality of life starts going down, that survival, the hazard of non-survival is increased? So a way to try to balance the two and relate the two processes, growth and survival, in a cancer trial setting. Again, this is described in a long 60-page report that we will post. In the meanwhile, I strongly recommend this book, Singer and Willett, Applied Longitudinal Analysis. Not only does it describe modeling change, that is growth modeling, but also event occurrence, which is their term for both discrete time and continuous time survival. And it's a very good book for non-statisticians because it gives a good balance between formulas and substantive thinking. So before they even introduce the statistical model, they give a words-only chapter discussing what kinds of things you might want to learn. What are the issues? And then they give a very good applied methodological description of quantities that are useful to look at, like this log cumulative hazard here, to determine the non-proportionality or proportionality feature. It's a thick book, but it's very good for both growth modeling and perhaps even better for one of the better applied books for event occurrence, that is survival analysis. So with that, we will then allow questions and some answers, and then we'll take a break and have a good setup for the final thrust of missing data.
Do we have any questions? Well, maybe. Oh, here we are, back here.
Slide 158. No, if everybody died, then we have information about all of them, so nobody is censored.
Oh, okay. So some survived. Where does the TC variable fit in the model? So say some people did survive. So there were people with 0, people with 1.
Yeah, so those who survive throughout, they will be censored at the end of the study, because they may die after the study ends, but they are censored within the time frame of the study.
Go ahead.
Two things. One, in the model where you allowed it to be non-proportional, is that like a piecewise proportional hazard? So it was proportional within the time segments? You made it a discrete time model here, right?
In this case,
Yeah.
in the continuous time?
Yeah.
Yeah, so it is piecewise, yes. Mm-hmm.
The other question relates to Poisson. Can you accommodate an offset variable for your count models? So
Yes, so an offset variable in Poisson has to do with the individual differences in length of exposure, right?
yeah.
And yes, so you read in a new variable which designates the length of exposure, and it's an X variable, and the regression coefficient is fixed at 1. Yeah, good questions. Yes, lady in the middle. Dama Sabachkoy. Almost. 135? So you have missing in the middle, and then they come back and have zeros?
Yes, or 1.
Well, in this case, you're only allowed 1, 1.
Right, but they may come back and they may be 0, 0, missing, and then that fourth observation could be 0 or it could be 1.
Yeah. No, in this case, you're only looking at a non-repeatable event.
Right, but
So it's
it
only,
might be missing in the middle.
it may be missing in the middle, and then they come back to zeros.
And then they come back and
Right, but then we know that they haven't experienced, we can assume that they haven't experienced the event.
Or
Yes.
they may have experienced it, for that fourth measure, you're counting on never had sex. You
Right.
can find them at wave 3, but wave 4
Right.
looking back and
Yeah, so it's a good question. Should you designate that missing period as having had the event or not?
right, or
It's like
did the model accommodate having missing in the middle?
Yeah. Well, I don't know that you can handle that very well because you don't have that information. But this reminds me that I should point out on our website is a dissertation by Catherine Mason, who after our initial paper went on and did a lot of work on this topic, and sits there on the website, and it goes through survival modeling that's not only of the non-repeatable event but recurring event kind, with those kinds of twists and turns. And she has a follow-up paper on that as well. So I would recommend that. Yes?
Slide 126.
126?
Could you describe again where under model missing the values after the x, so 0.4, 0.8, 1.6, 3.2? What,
So how,
yeah, what are those? How should that refer to?
Yeah, so this should be these are logistic regressions where the dependent variable is the probability or the logit of the probability of having missingness at that time point. So these are logistic regression coefficients, and we see that they increase over time. And Linda referred to this as being MAR missing, and where we will define what MAR is after the break. Okay, it looks like you're ready for coffee, folks. And come back for the thrilling missing data finale. All right, let's get started again for our last block. And Linda says hello to all of you. She's heading back to LA to field customer support, whereas I'm staying on the East Coast for one more day, heading up to down to DC, I guess it is tomorrow. So I'll be your only host for this remainder. And we're going to devote it to a fun topic of missing data, which is a very rich topic where there's a lot of statistical research activity. Linda talked about already, used the words MCAR and MAR, and now we're going to understand what they were. So we're going to take a look at missing completely at random. That is, variables have missingness by chance. I'm on slide 167. It typically only happens really guaranteed when you have missing by a randomized design. So for instance, you have two tests, two versions of a test, and you randomly say this group is going to get that test, this group is going to get that test. Then everybody has missing data on the other test, but the missingness is totally random. Perhaps multiple cohorts, assuming a single population, can be that you saw that staircase drawing that we had, colorful on the left. Perhaps that can be a MCAR situation, missing by design, as an example of that. Missing at random, that's a very useful concept, and it is one that is the standard workhorse for all software that is out there. It says missing at random, but once again, the term is made up by statisticians. They're not that pedagogical often. Because missing at MAR, missing at random, means not missing at random at all. It means that missingness can be totally strongly related to observed variables. So that's why Linda was having that simulation where the X value of a person, background characteristic of a person, influence that person's missingness. And that's a very selective missingness, right? So if, for instance, you have missingness if your age is high. But if missingness is only explained by age and not by other unobserved things, you have things under control. You're in the MAR situation, and therefore your software will give you the right answers. You only really know that you have MAR when you have missing by selective design. Selective design has another term in behavioral science applications. as a screening test. So you have an instrument to measure if a group of individuals has a problem or not. If they have a high enough problem level, then you decide to continue to study them, to continue to observe some things, some Y in a growth model, for instance. But if they fall below that value on the screen, then you don't observe their Y values, and therefore you have missingness. But it's missingness that's planned. It is not MCAR, but it is MAR type of missingness. That's still very much okay. The difficult part is when you have so-called non-ignorable missingness, which is, there's a bitter fight here, bitter fight between those who want to call that NMAR and those who wouldn't call it MNAR. Yeah, I can hear you can appreciate the seriousness of that debate. Not missing at random or missing not at random. Anyway, that is the case where missingness is related to values that would have been observed. Values that you don't have. So you have, let's say, a Y star value, a potential value, the level of sickness that a person has, and the interviewer comes to the door, knocks on the door, and the person does not open the door because the person has a high value of sickness. So that Y star value behind the door remains unobserved, but if the person had opened the door, Y star would have been observed as Y. So missingness is related to the value that would have been observed. So that's a latent value, a latent variable, and missingness related to latent variables is non-ignorable in most cases. So the tricky thing here is that we can test to see if we have MCAR, but we cannot test to see if we have MAR or NMAR. There is no test of that, unfortunately. But that means that there is an open field for trying out a lot of different kinds of NMAR models as alternatives to the MAR model, thereby doing a so-called sensitivity analysis to see if the NMAR models would give any different results than the MAR model results. A very good book on this is Little and Rubin, 2002. It's written for applied statisticians. There's a new book coming. Have you heard of that? Craig Enders at ASU is coming out with a book on missing data modeling, which is more applied, that is a higher ratio of words to formulas than Little and Rubin. And I think it's a book that'd be appreciated by many non-statisticians. And you may want to get that. I think it's going to be announced any day now. Now, a couple of issues regarding types of estimation here. You've probably heard about list-wise deleted samples. So if you have a growth model for Y, list-wise is getting rid of anybody who doesn't have data at all time points. List-wise is deleting any person who didn't have observation, who wasn't observed at all time points. So if you have missing data at only one time point, list-wise would delete you. Let's contrast that behavior, list-wise behavior, with the missing data situation. If MCAR is the situation, if MCAR is true, parameter estimates and standard errors are consistent. That is, they're okay. Parameter estimates and standard errors are okay, but estimates are not efficient. That means that the standard errors are unnecessarily large, as you might imagine. Inefficient means standard errors are unnecessarily large. That is, sample size gets depleted by list-wise deletion, therefore the standard errors are too large. That's under MCAR. That's the best possible circumstance for list-wise, because if MAR is true, but not MCAR, so missingness is predicted by observed variables for the individual, parameter estimates and SES, standard errors, are not even consistent. They are wrong. So list-wise deletion often gives incorrect results because very often it's reasonable to assume that you don't have M-car. Maximum likelihood uses using all available data. What about that? So in the growth model, you use everybody's data point, even if they're only observed, say, at the first time point, y1. Well, let's take that tack. Well, when M-car or MAR is true, parameter estimates and standard errors are consistent and estimates are efficient. So that seems to be a good approach. Maximum likelihood using all available data. And that is really, as we will see, the approach that's taken by standard software. So MAR is more flexible than M-car, so we can really say that when MAR is true, the maximum likelihood approach would be one of using all available data, and that is a good approach to take. Now, when you have this non-ignorable missingness, then you have to get into other kinds of models that we're going to talk about at the very end today, called selection modeling and pattern mixture modeling. So I'm going to talk a little bit about that as we end. And by the way, before I forget, as some of you have to leave early, a note tells me to please remind everyone to put their badges in the boxes on the tables in the back. Let me repeat that. Put your badges in the boxes on the tables in the back. And also, please exit quietly. You may not have heard this before, but there's a reception in the gallery. And in fact, we have permission to stay in this room past 5. I'm going to end right before 5, but I'm going to be here so we can talk, so we don't have to go out and talk outside where the echo is that they worry about. So anyway, that's that. Where were we? Selection and pattern mixture modeling are NMAR activities that we're going to learn about today, just before 5 o'clock. And that still uses maximum likelihood estimation. I'm also going to tell you a little bit about imputation, which is another approach to missing data. It means calculating, estimating values for the missing data. So estimate each person's missing data. That's an imputation. And you can do that with various techniques. For instance, instead of a person's missing value, you can insert the mean of people who have observed data on that variable, or you can you do a regression between two variables and predict what the value would be for the missingness. It's not a good approach because it tends to give an underestimation of variances and covariances for that variable and other variables. And instead, what's the preferred approach these days in the imputation area is so-called multiple imputation. Multiple imputation. It's a Bayesian approach, so we do Bayes analysis instead of maximum likelihood. So it's a totally different framework for inference. And it's essentially creating, instead of creating one data set where the missingness has been estimated, you create several data sets. So each person's observation on a certain variable is given several different values, several different imputed values, which will give you then a feeling for the instability, the imprecision in the missing value estimation. And that's what they are after in this context. So there are several programs dealing with multiple imputation out there, and several different multiple imputation techniques. I'm going to talk not about imputation hardly at all today, but I'm going to talk about MAR, and I'm going to talk about selection and pattern mixture modeling. And I'm going to go to, we have a lot of slides here, and I'm going to try to focus on the most important ones. Let's take a look at slide 173. Well, actually, let's look at slide 170. I just can't skip this one. Because some of this methods teaching is directly related to design issues. And I don't want to miss the opportunity to encourage you to think in more modern ways of designing your studies and how you measure things. And one example was before the break. If you do longitudinal studies, don't hesitate to change the items across time, but when you change, don't change all of the items from one time point to the next. Keep some of the items the same for adjacent time points if you can. Somebody was telling me about the ECHL study, the Early Childhood Longitudinal Survey in Education, where apparently they keep changing the measure over time. And their argument is, well, we studied these kids so far apart, we can't have any item the same. Well, then the problem is you can't study change. So you should have measured more frequently where you could have had some items the same across time, a fatal design flaw. Here's another example, if I understood that correctly. Here's another example. Let's say that you have a model where you want to, it's really a structural equation model. You want to predict Y3 here. And you have the notion that the covariate is actually a latent variable. And it is measured, it's measured by various kinds of indicators. So I think the example here is that this is a health outcome, and this has to do with diet, what your diet is like. And you have one measure of diet, say a questionnaire that you answer, which is a measure of the true diet. But for part of the sample, you have a second measure, which is perhaps a better measure. It's a dietary diary. So you have two indicators, and with two indicators, you can actually identify the factor and identify the structural slope here for the true covariate. But this dietary diary is more expensive to administrate, and you don't have to give it to everyone in the sample. You can randomly use a subset of the sample, these people up here, for whom you get both Y1 and Y2, whereas for other people, you have missingness on Y1, on the expensive instrument. Perhaps you only use both instruments for 20% and have 80% missingness here. But it's totally random missingness. And therefore, all you have lost is a little bit of efficiency so that the standard error of this structural slope that you're primarily interested in, standard error is going to be a little bit larger than if you'd had both measures for everyone. So that's an example of an MCAR missing by design situation, which leads to design possibility for measurement, for saving money. And this idea is often used in education where you have so-called matrix sampling, bib spirals, where not every student, where different student groups get very different test items to solve. So you have planned missingness. So let's look at this. Here's an interesting case which sort of is the essence of the MAR advantage over listwise. So look at this data matrix, bottom left. You have two columns, X and Y, two correlated variables, X and Y, and you have two groups of people, NH and NL. And NH, these people in this top box, they have complete data. They have data on both X and Y. Those are the people you would use if you did listwise deletion. Whereas down here, for these people, you only have data on X. You have missing data in the shaded area for Y. And let's say that the missingness is loosely related to the level of X. So for low X values, L down here, for low X values to the left here of this squiggly line, you tend to have missingness on Y. but for high x values, you have observations on y. Now, what we're going to be interested in is to estimate the parameters of x and y. So, for instance, if we assume multivariate or bivariate normality here, how many parameters does that give us? 2 means, 2 variances, and 1 covariance. 5 parameters, right? So say that we're interested in estimating the 5 parameters of this bivariate distribution. 2 parameters are of particular interest. Then say that we are interested in the mean and the variance of y, the mean and the variance of the y variable. The interesting thing here, the crux of the matter, is that if you're interested in the mean and the variance parameters for y, it is useful to use information on x, even if you don't have y. So using this little square of people, those people's x values, will help you estimate the mean and the variance parameter for y. You're likely to do better in the estimation of those y parameters if you use all available data, not only this box of complete data people, but also this box who have only x information. Use all available information. And that's what's illustrated here. Let's see where we should look. Let's look at the bottom. Let me do this instead. Let me go back here and go forward here. That was the forward is this way. That was the intuitive way of saying it, but in formulas 58 and 59, we show how that intuition plays out. Say that we want to estimate the mean of y, mu sub y hat, the estimated y. We're going to, MAR says that you should estimate that y not only by y bar being the sample mean for the people in the complete data group. Y bar is created from this part of the data box, right? The complete data people. This is what you would estimate the mean of y if you use listwise. It would only be correct if you have MCAR. But under MAR, that listwise estimate needs to be adjusted by beta hat, which is the regression coefficient for y on x, saying how strongly related they are, times this adjustment factor, which is the estimated mean of x minus x bar. Estimated mean of x uses all people minus x bar being the people with listwise. So 2 estimates of the mean of x using everybody and using those who have complete data. The difference there, multiplied by the regression coefficient, is how you want to adjust the listwise present estimate to get the MAR, maximum likelihood estimate. And if you think through this diagram here, you will note that that is the right kind of adjustment to make. And that's what this low and high distributions illustrate. But I'll leave that to you as an exercise to see that that's the right kind. You will have to reason which is highest, the estimate of x for everyone versus the estimate based on listwise. Listwise present was the NH group, those who tend to be high. Well, that sounds like x bar is higher, and then mu hat, which means that this is negative, which means that with a positive relationship between y and x, we're going to downweight the y bar, and then you have to reason about, does that look reasonable relative to the figure? Leave that to you. Anyway, that's what MAR does. Very smart move by MAR. It adjusts it in the right direction and gives a new estimate. Same for the variance of y. This is the variance of y in equation 59. It takes the listwise present variance of y and adjusts it by a beta square factor times the difference in the variance estimate for x using everyone versus using only the listwise present. So that special case, bivariate case, illustrates what MAR does. It, by using all available data, it gives better estimates. And paradoxically, better estimates for a variable y by using information on x down here. That's the extra information that maximum likelihood under MAR uses. Using all available data is therefore the right thing to do. So when you do maximum likelihood estimation in Mplus, when there is missing data, Mplus automatically uses all available data and does an MAR analysis. So Mplus will give you these mu hat and sigma hat parameter estimates automatically. We used to have listwise deletion as the default, but because that was much faster to compute. But nowadays, computers are so fast and the program is so fast that we have MAR as the default. Now, MAR is a standard assumption, but it's not always a correct assumption. But you can actually make MAR more plausible. You can make it more plausible by including, if the model includes covariates that predicts missing data. So a longitudinal study, for instance, people may stay in the study longer, have less missingness if, say, they are more highly educated, older rather than younger, I don't know. So if you have covariates in the model that influence missingness, then MAR is made more plausible. Because as long as missingness is related to variables that are observed for the subject, MAR holds. Now, there's always a part of the missingness prediction that's due to unobserved covariates. We can't get them all, but the more important covariates we get, the better. However, some of these covariates may have no substantive role in the model. Some of these covariates may not be important for the growth factors, for instance, but only for the missingness. So we say then that correlates of missingness, correlates of missing data may not have a causal role in the model. That is, they don't influence the dependent variables. And if you include them as covariates, then it biases the model estimates. Because then your true covariates that have substantive meaning, that have a causal role, become partial. Their coefficients become partial regression coefficients with these extra missing data covariates included. And that's not what you want. Two approaches to solve that dilemma. One is the Bayesian multiple imputation approach. The other is staying with maximum likelihood and doing a little bit different modeling. The multiple imputation approach is such that you can actually work with two different sets of observed variables. One set of observed variables for the imputation model and another set for the analysis model. So for instance, very often, the imputation model can use more observed variables, only some of which are relevant for the analysis model. So you can include in the imputation model variables that are related to missingness, but play no role in the substantive model that you're interested in. And that's possible because you do the analysis in two steps. First, you do an imputation step. You get the missing data fix-up, missing data estimation in multiple data sets, and then you analyze the model. By the way, Mplus 5.21 has a way of reading in multiply imputed data sets and doing the analysis then for each of the repeated data sets. That's what you do in the analysis part. And then averaging the parameter estimates over those different data sets and computing the standard errors for those model parameter estimates. Not the average of the standard errors, but you have to use a little bit more elaborate formula, including both the average standard error and the variation across the imputed data sets in the parameter estimates. So it's sort of a within and between variation that has to be factored into the calculation of the standard error. So that's done automatically in Mplus current version, where the data is type equals imputation. You even have, and I think this is unique, you even have a model test of, chi-square test of model fit for these multiply imputed data. Now, staying with the maximum likelihood framework, you can include these missing data correlates. I call them correlates. That is, it's variables that don't have a substantive role in the model, but only have a missing data role. Not as X variables that we talked about up here, but as Y variables, freely correlated with all other observed variables. And it's a recent overview of these kinds of techniques in Schaefer and Graham, 2002. It's, again, a Psych Methods article that you can take a look at. I'm going to get back to correlates of missing data a little bit later, but I want to point out something that comes up quite a lot on Mplus discussion and in the support questions. And that's missing on X. Very often missingness happens for X's. And if you delete people with missing on X, you can deplete your sample quite a lot. So it's very hard to get everybody to answer all of the questions regarding their background. Now, the regular modeling that we look at concerns Y given X, the distribution for Y given X. Like in regression modeling, we're not interested in the modeling of the covariates. We just let them be freely correlated. So the marginal distribution of X is not involved. We don't assume anything about it. We don't have to assume normality, for instance. And that's fine if there's no missing on X, in which case, considering the conditional distribution gives the same estimates as considering the joint distribution. And that's why structural equation modeling programs typically work with a joint distribution, even to the point of estimating parameters for X, which is not necessary. So with missing on X, continuing on the next slide, ML under MAR must make a distributional assumption about X. When you want to handle missingness, you have to make a distributional assumption, typically non-normality. So the modeling then concerns the joint distribution, both the conditional times the marginal. And with missing on X, that means that we've expanded the model, a model that makes stronger assumptions than the one we started with. It's a model that says something about X, distribution on X as well. So you shouldn't do that lightly, but it could be done in Mplus by bringing in what we call this bringing in the X variables into the model. The way you bring them into the model and do this joint analysis is by mentioning some parameter related to them. So for instance, if you have Q X variables, you can mention their variances, X1 through XQ. Just say that, and suddenly the variables would be part of the model, the joint modeling here. And we will make the normality assumption on X, which is often the assumption made when you work with multiple imputation. It's not innocuous, but it's certainly not non-standard as well. So missingness on X can be handled in this simple fashion in the maximum likelihood framework. Now, there are perhaps better ways of handling missingness on X using multiple imputation, because then it's easier to take into account the scale type of X. Some of the X's are dummy variables, for instance. I'm not going to go through these pages, 179 and onwards, but those of you who are statistically minded can penetrate them and get the definition of MAR in a more detailed statistical sense. What these pages say, 179, says that the data that you observe is not only Y and X, but also M. The data that you observe is not only Y and X, but also M. What's M? M is whether or not a variable is missing. It's a binary variable. It's a variable too. We just can't, the fact is that if MAR is true, we can ignore that variable in our estimation. We can do the modeling of Y and X only. We don't have to worry about M. But before 5 o'clock, we're going to bring M into the picture. But 179, 180 is for your own studies. Let's take an example instead. Back to the AMPS data and get you familiarized with the Mplus output. So back to the AMPS modeling, the alcohol misuse overall variable at 4 time points. And as you can imagine, there's missing data. We're going to do an analysis here where we do a growth model. And we're going to ask for patterns of missingness. That output option is quite useful. You can even use it when you do a type equals basic analysis before you do the growth modeling. And here's what it says. Slide 185. You may want to make a little note here that these X's, X means data not missing. So X is present. The empty spots means missing. X means observed. And in these data, there are 15 different patterns. They are numbered like this. Pattern number 1, you have X's for all 4 M over time points. That is, these are the complete data kids in pattern 1. 685 are complete data, 685. And then you have those who dropped out after the 3rd time point, a missingness on the 4th. There are 143 of them. Pattern 3, we would call intermitting missingness. They have missingness at the 3rd occasion, but come back from the 4th. There are 73 of those. Pattern 4 is, again, a dropout pattern. They drop out after the 2nd time point, etc. onwards. So you get a feeling for where the missingness, which variables have missingness and what kinds of patterns are common patterns in the data. So that's quite useful. And then you have this covariance coverage table, which says that, for instance, it says that at the last time point, if you look at the diagonal first, the last time point, 68% of the sample remains. 68% of the sample is there at the last time point for M over 3 measurement. So you see here the coverage is a little higher at the previous time point and higher still at the time point before that. And now the coverage at M over 0 is 46. 46% of the sample has M over 0 observations. That was because the review committee, in its infinite wisdom, decided that this intervention study was not going to be funded to observe everyone before the intervention started. Only half of the people in the study would have a baseline value. And you can imagine what I think about that, having talked about baseline, the importance of baseline. So there should be 50% here, but then you have some missingness, 4% missingness among those who should have been observed. And then you have the pairwise coverage. So 31% have observations on both m over 0 and m over 3. And these covariance coverage values have importance for your analysis. Of course, you want to have high coverage, low missingness, because otherwise, if you have a lot of missingness, your modeling results would rely too much on modeling assumptions, such as normality, instead of actual data. And in fact, when you estimate the H1 model, the unrestricted model, which will give you the chi-square, the regular chi-square for this growth model, you actually have a hard time estimating the variance-covariance matrix if you have low coverage. For instance, if it said only 0.05 here, only 5%, you would have a very hard time for this algorithm to converge to an estimated value. The minimum coverage value in Mplus, we warn people if they have less than 10%, because it's been found that this so-called EM algorithm, expectation maximization algorithm for maximum likelihood estimation of the H1 model, runs into trouble when you have very low coverage, so we give that warning. But that's a very important sample statistic to look at. Here you get the test of model fit. We're not so interested in the growth model results here, as we are, we're interested in this picture. So tell me why these two lines are different and what that means. Why is the MAR line, the estimated growth curve under MAR, lying higher, lying above the estimated growth curve under listwise? MAR contains more useful information as one vote, more votes. Who has lower alcohol scores? The people who are missing have higher alcohol scores. Yes, that's right. You're both right. Those who are listwise are the children or youngsters who are present at all time points. So they have perhaps less truancy, better behave, therefore drink less, perhaps. That's why. Whereas MAR uses everyone who has at least one time point here, and therefore includes children who are perhaps behaving less well and are higher on the M over. So that's what the direction you would expect. So it makes a difference. Here's a section, missing data correlates using ML, that I'm going to skip because you can watch the movie. This one actually is in Camtasia format. That is, you watch it on the screen, you see a picture, and you hear a voice. And it's illustrated. It is referring to writing here in psychological methods. SEM is the structural equation modeling journal. Various kinds of overview references. And Craig Ender's book will also talk about using missing data correlates. Again, it is variable in trying to incorporate variables that correlate with missingness, even though they don't have a substantive role, to make the maximum likelihood estimates under MAR be better. So I'm going to skip these pages. And we have a technical report sitting under technical appendices, I believe, on the Mplus website, where we describe how Mplus has automated the missing data correlates approach that these authors talk about. So essentially what Mplus does is it brings in the missing data correlates as extra y variables in the model. And there's supposed to be extra y variables in the model that are correlated with all the other y's. So Mplus does that automatically for you without throwing off your number of parameters, degrees of freedom, and chi-square test of model fit. The one reason I don't spend more time on it is that the experience I've had to date is that it is quite difficult to come up with missing data correlates that make a difference. Because they have to be strongly correlated with missingness while not strongly correlated with the observed variables that are in the model. And that's a hard thing to accomplish. So let's put that aside now. There are more important things to talk about, I think. And instead, let's focus on slide 200 here for a second as just a segue to what's coming. You would think that it's very easy to estimate a mean for a variable. But with missingness, that's no longer true. Take, for instance, the mean of the LSA math score at grade 9. It can either be that high, that low, or somewhere in between, depending on which method you use. This is how high it is if you use everybody who has observations on math score at grade 9. Everybody who has observations at that point. If you use listwise deletion, it comes down. And if you use ML under MAR, it comes down further. So let's think about that for a second. Here is all available, max n, all available people at that time point are used. MAR, so you estimate the mean using only the grade 9 score. But MAR, what does MAR do? Well, MAR can use information on the means for the other time points as well. So if you have missingness on this on grade 9, you can borrow information from grade 7, 8, 10, 11, and 12. In line with the first example of y regressed on x, that x values observed in the data actually helped you estimate y parameters. So who's to say what the best estimate of the mean is? Is it there or is it there? Well, I would pick this, because you borrow information from a neighboring measurement locations. So why is the MAR score lower here than the max n score? Yes, Michael has a answer.
It looks like the observed max n values later are lower, suggesting that there's kind of a borrowed data you're going to drag down the mean.
Yeah, maybe so, maybe so. If you look at the bottom here, you have the max n sample size varying across the different grades. So we're working with the 2040 here. We're working with the 2040. So those 2040 people are certainly different than the MAR people, which is everyone in the sample who has an observation on some point. So these people who are present here, they're not dragged down by people who are low at other time points, is maybe one way of looking at it. They're not, that estimate is not pulled down by using information at other time points that have lower scores. So in any case, it illustrates that you have a real task to estimate a simple thing as a mean when you have missing data. And again, I would use the MAR using all time points, even if you're not interested in the growth model. So let's see. I'm not going to talk about that. I'm going to talk about non-ignorable missing data for the rest of our time together. Because I think it's time that we move into this era of going beyond MAR. And there's a big literature on this. You have the same thing on the two slides. You have the Little and Rubin book. And soon you have the more accessible for the non-statisticians, the Craig Enders book. There's been recent writing about that in the handbook chapter. When I say handbook chapter here, I refer to the handbook on longitudinal analysis by Fitzmaurice and others. It's in the reference list, I believe. We're going to make a distinction between selection model and pattern mixture modeling, and a third approach called selection modeling, called shared parameter modeling. Selection modeling looks at the data in this way. You have your outcome. Think growth modeling now. You have an outcome over time. You have covariates. But that's not the only data you're observing. The other data that you're observing is whether or not you have missingness on the y. Talking about missingness on the y here. So missingness or not is a binary variable for each corresponding to each y variable. Selection modeling looks at y given x and missingness given y and x. That should be contrasted with pattern mixture modeling, which looks at missingness as a function of x and y, the outcome, as a function of missingness and x. In both cases, you're looking at the full distribution here of y and m given x. But in one case, you're looking at m given y, and the other you look at y given m. Two ways of expressing the same joint distribution of y and m, but leading to different kinds of models. So you have a classic Diggle and Kenward approach for selection modeling, and a classic pattern mixture model approach under pattern mixture modeling with variations here. Final third kind is a shared parameter model. Here I'm dropping x so that the joint distribution of y and m is expressed as m given c and y given c. So you have a latent variable c which is in common with m and y. And in this case, it's a latent class variable. So you model the two, you can think of this as two processes, y and m, and they are tied together by both being dependent on a latent variable. So that's just a general modeling overview. Let's take an example. Let's take an example that has to do with an antidepressant trial. And this is in that paper that I gave you a PDF for, 205. And we're going to make a distinction between, in longitudinal data, a distinction between intermittent missingness versus dropout. And we looked at the patterns of missingness to say what the difference was. Intermittent missingness in longitudinal studies may be a less dangerous situation. It might even be MCAR, but dropouts could be MAR or may require NMAR modeling. So in this new paper that I submitted, we try various kinds of NMAR alternative to the MAR modeling, MAR modeling, for a antidepressant trial. So we have here one of the largest antidepressant trials, I think maybe the largest in the US, 4,000 individuals, STAR-D, NIMH supported, multi-site. where subjects are treated with the antidepressant citalopram. There's not a placebo group, but you look at the treatment and see, look at the drug effect and see how that influences depression. We are going to look at the clinician-rated depression score measured at baseline and weeks 2, 4, 6, 9, and 12. Turns out that 25%, only 25% have complete data through the 12 weeks. 60% have monotone dropout, monotone missingness, which is another word for dropout. 14% have non-monotone missing data patterns, which is another word for intermittent. So most of them have monotone dropout missingness, and that's what we're going to focus on. Coverage, a baseline 100%, after 2 weeks down to 79%, 69, 68, 57, and only 39% at the 12th week. Now the reasons for disappearing from this level 1 are some of these reasons are more or less under the control of the experimenters. One reason is remission. They're moved to follow-up. Remission meaning, simply put, they're being cured, and they move to just being observed, but no further action is taken. That is, they have been cured, and they could be removed from the study after a couple of weeks if the depression. Usually, remission is defined as falling below a certain level on the depression score. In this case, I think it was 5. They can be moved to level 2 if the medication is inefficient or not tolerated. Level 2 means that they get put on another antidepressant. But they also disappear from the study. And then they have the people who disappear from the study for unknown reasons. And here you can do an interesting plot corresponding to these different situations. And this is a plot that we now allow in Mplus version 6 automatically. So you have the total sample here. It's interesting to understand this plot. On slide 207, you have the weeks on the x-axis and the depression score on the y-axis. Low value means low depression. And you have the overall development over time. Depression gets less and less for these individuals. But look at the triangles. So look at that triangle, for instance. That is the average depression for those who drop out at the next time point. So it's an interesting way of plotting the data, right? So it's the mean of the people who are there up to this point, but then drop out at the next time point. Which suggests that they drop out because they have high values. So the medicine was not efficient. And that's for the total sample. And you can actually break it down into those who left, who were moved to the next level. That is, the medicine didn't work or they had intolerable side effects. Yes, there you drop out because you are high depression. As opposed to those who leave the study because they remitted, they were cured, they moved to follow-up. They drop out at the next point because they have very low values. They're removed if they go below 5. That's remitted. So they leave the study if they're below 5. Whereas here they leave if it doesn't work and their depression is still high. So it's a way of looking at the data. So this is sort of the endpoint characterization of the patient. They're either moved to the next level or to follow up or they exit the study. All those three are reasons for missingness, and that is not being observed through week 12. So if you want to do a growth model for the development through week 12, we have to take this kind of missingness into account. And it is not missingness that is explained by the observed variable, because in this case they drop out because of the depression that they felt after the last measurement. Here they drop out because they have a low value, but not on the outcome of our kids. They're actually using a HAM-D variable to decide on the follow-up decision. So we're going to do NMAR modeling here, NMAR modeling. We're going to do NMAR modeling and MAR modeling. We'll say that clearly. And we're going to start with selection modeling, which I expressed statistically, which may not have been totally clear for people who don't think in those terms. But let's do it in pictures instead. Here is selection modeling. If you remember, selection modeling is modeling missingness M as a function of Y. Let's break that down. We're now going to talk, we can talk about M as a missing data indicator, but let's now focus on dropout. So we change from M to D. So dropout is D. So dropout is D here. It's influenced by Y. We're going to disentangle this model into details. D is the dropout or not. It's a binary variable, dropout or not at these different time points. And it's influenced by Y. So that's the selection modeling idea. We're saying that this is a logistic regression. These are logistic regressions, binary, dependent variables. And you note here the basic idea that we're no longer analyzing only the Y's. We're analyzing the Y's and information having to do with missingness. That's how you get past MAR, that you bring in information about the missingness in the model. So Diggle and Kenward suggested this model, which is understood as follows. Dropping out after the first time point, after baseline, this is baseline, dropping out after baseline is predicted by the baseline value. If it was only predicted by the baseline value, this would be MAR, right? Because baseline is observed. And we said if missing is related to observed variable for the person, that's MAR. But it could be that dropout is also a function of Y1. And Y1 is unobserved for those who dropped out after baseline. And so we have a new feature here. A variable can be observed for some people, those who didn't drop out after baseline, or a circle for the people who did drop out after baseline. And for those who did drop out after baseline, the circle is really the Y star I was talking about, and it's that latent Y star variable that we didn't get to see, that higher depression that also predicts dropout. So if this arrow is significant, then MAR is violated. This is MAR, but this is, if this is present, we have NMAR. So this is, advanced modeling, but should be accessible. So what do you do in Mplus? Well, you just say ISQ. We're going to see the inputs, measurement model here. I'm sorry, growth model. And then you add D on Y in this specific fashion. And out comes different growth parameter estimates than you would have under MAR, MAR being analyzing only the Y's. One feature here that's interesting, given your extensive, given our extensive treatment of survival analysis, I'm being ironic here, is that these are scored as survival indicators, meaning that we're going to do this analysis, this regression here, in the fashion that these D's are scored as event history indicators. So 0, 0, and then 1 dropping out, and then missing. So if you drop out at before time 3, you have 0, 0, 1, missing. So So you have the survival scoring that we used for the U's. And that's what you need to do Deagle-Kenward selection modeling. So that means that the risk set is those who haven't dropped out before. They are considered as the risk set for dropping out thereafter. Well, I should say also on the right is a more recent 2008 variation on this theme, where the dropout is a function not of y, but of the growth. So if the growth is going towards higher depression, that tends to influence the dropout tendency. And you can have a mixture, growth mixture model in here. So that is the Bunkins et al. Selection modeling variation. But I'm not going to talk about that today. Here's how you set up Deagle-Kenward with a simplified, well, first of all, the variables are these D's. The use variables are these dropout indicators. And they are declared as categorical because they are dependent variables. The D's are dependent variables, so we declare them as categorical. They're binary. And now we're going to have a new feature in version 6, data missing, where for the y variables that we consider, we're going to define a set of binary variables. They are defined D1 to the D5, defined from the y's, from missingness on y's. We automatically determine these dropout indicators of the type survival dropout, S dropout. So scored 0, 0, 1, missing, missing, missing. So the survival binary Ds are created here by data missing automatically, saving you a lot of mistakes that I went through. And then you do a maximum likelihood estimation. And I'm not going to say so much about the technical parts of that, but let's consider the model that you work with, slide 210. Quite doable analysis, doesn't take too long. You have the growth model as usual. That's what you have at the top left. And then you have the D on Y set of relationships. D1 on Y0, D1 on Y0, and Y1. D2 on Y1 and Y2, etc. down. And you see that you have equalities here, so that if the lagged effect is called beta 2, you know, dt on yt minus 1 is beta 2, and the concurrent effect is beta 1. That is the standard Deagle-Kenward assumption, simplifying the model. So if beta 2 is significantly different from 0, that's okay, because that's the MAR approach. That's the MAR missingness, an observed predictor. But if beta 1 is significantly different from 0, then MAR is no longer the case. So it's the allowance for beta 1 effects here that makes this an NMAR model, not missing at random. So you can go home here and do this on your own data. And actually, you have the setups. This is from this paper that I mentioned. You have the Mplus setups for them on the Mplus website. And you can do this analysis also in version 5.21. The only thing is that you don't have this data missing simplification, but you could do that by a series of defined statements, and you have the version 5.21 setup for that as well. So that's one type of non-ignorable missing data modeling. Here is another one, which is perhaps even more common. And you see the distinction here between selection modeling and pattern mixture modeling. On the left, the dropout information is a dependent set of variables predicted by Y, which is very relevant. Why, if you're depressed, medicine doesn't work, you drop out. That makes sense. But pattern mixture turns it around. I think this is Rod Little's favorite. Missingness influences Y So the arrows go in the other direction. And the D's have to do with dropout, but the D's are no longer survival scored. They're no longer 0, 1, missing, missing. They are regular dummy variables. They are 1 if you dropped out here and 0 elsewhere. 1 if you dropped out there and 0 elsewhere. Standard dummy variables. And the idea is that for different dropout patterns, those who don't drop out versus those who drop out the last time point versus those who drop out after 2 time points, they may have different growth factor means. They may have different growth factor means. So if you look at the complete data people, they have different means than those who dropped out after the first time point, or after the 3rd time point, perhaps. And this model allows that. It allows the model to be slightly different for different dropout patterns. And you can also have the variances of the growth factors differ as a function of the dropout patterns. But here we stay with the means only. So that is a model then that could capture non-ignorable missingness. There is a variation on that, just like there was a variation on the Kenward model, which has to do with mixtures, and that's Roy's latent class dropout model. Instead of having, in this case, you have 6 different patterns of dropout and not dropping out, 6 different patterns. You could summarize them into, say, only 3 or 4 patterns using a latent class variable. This model then will be more understandable in August. But Roy, you have the reference there, came up with this model as a better model for of the pattern mixture kind than the conventional one. And that one is also easily done in Mplus. And my experience is that it usually fits much better than the conventional one. So pattern mixture modeling, how do you do it in Mplus? I'm talking about the conventional pattern mixture model here. But again, the use variables being the analysis variables, are not only the Y's, but the D's. But in this case, as opposed to selection modeling, we don't declare the D's as categorical because they are X variables here. We use the new version 6 feature of data missing, creating those binary variables automatically from the Y's, depending on whether and when they are missing, to create these dropout indicators in the dummy dropout version, as opposed to the survival, so the D dropout like that. So it's quite S dropout and D dropout are the 2 settings quite conveniently. And then, again, the growth model is the same as you have on the right. It sits at the top here. How simple life was this morning, right? Or yesterday morning, rather. And now you regress all of those growth factors on the D's. With some variation here, I mean, you want to say ISQ on D1 through D5, right? But you have to remember that those who drop out after baseline, they cannot give you any information about the slope and the quadratic terms, because you only have 1 time point. Those who drop out after the 2nd time point cannot give you any information about the quadratic. So we have to impose certain restrictions, saying that, and this is using the adjacency argument that's used in pattern mixture modeling. I'll give you references so soon. Well, here, this is a cumbersome way of saying that I can be regressed on D1, D2, D3, D4, and D5. No problem. S, however, For those who drop out after the first, they have to be held equal to those who drop out after the second to get to use 2 time point data. Q has to be held equal to, whereas S on D3 can be different. Q has to be held equal across the first 3 dropout pattern to draw on the information here, those who drop out after D3 is after having 3 time points. So you have to have these equality restrictions on the model. But other than that, it's a standard pattern mixture approach here that you do in Mplus quite easily. Here, for completeness, I also give the Roy 4-class latent dropout model, but again, it belongs better in the August treatment where we know about mixture modeling. But it turns out that the 4-class model fits much better than working with all 6 possible dropout patterns in the conventional pattern mixture model. Now, when you have done this, say that you do this selection modeling. Say that you do selection modeling. What's typically then reported is the growth curves under MAR and the growth curves under, say, Diggle-Kenward. And here is the Roy version of the pattern mixture model. So you draw a picture like this. MAR is the lowest here. And Roy and DK, these are the two. This is Diggle-Kenward selection modeling. This is Roy's latent class version of pattern mixture modeling. And they tend to lie a little bit higher. Why is MAR the lowest curve at the end? I don't know if you have energy to penetrate that. But if you remember, it has to do with the dropout means that we looked at earlier. MAR, towards the end, MAR tend to, well, towards the end, the people who are missing tend to be of the kind that they have a high depression score. And although MAR tries to borrow information from earlier time points, it cannot do so successfully enough, is what the NMAR alternatives of DK and Roy give. So you have a bit of a difference here. Now, I would say that, yeah, that's interesting, but it's not that interesting. So what if we instead take a look at what the Roy pattern mixture model actually says? That is, it's a pattern mixture model that summarizes different dropout patterns going from 6 to only 4 classes of individuals. And lo and behold, you are now looking at your first growth mixture model that we will deal with in August. Roy didn't stress this, so I try to stress it in this paper of mine, because this looks like, although he was trying to summarize dropout patterns, I think what that model really stumbles into is depression trajectory class patterns. These are very interpretable patterns from the antidepressant trial point of view. This class, green, are the individuals who respond to the antidepressant citalopram. 43% are in that class. These are the people who don't respond, 28%. And then we have an interesting class of 18% who have a temporary improvement, but then worsen. And one can argue what that means. placebo responders, that is, they respond not to the drug, but to the attention of the environment, the doctors and the nurses and the staff, but only up to a point. After 6 weeks, the joy of that is gone, and the depression keeps going up again. The interesting thing is, though, that these people, some of these people, have a low trajectory, a lower, this is the average, have a lower trajectory, and fall below 5, and are called remitters. So whereas they will tend to worsen afterwards, so they may, in fact, need a different drug. This was perhaps just a placebo response. They needed a different drug, but we don't see that because we took them out of the study. This is, here you're looking at a growth model under, that goes beyond MAR. It's an NMAR model drawing on a special kind of pattern mixture model that I just called Roy pattern mixture modeling. Interesting thing is, though, if you do an MAR analysis of these data, a growth mixture MAR analysis allowing for 4 classes, 4 different types of development, you get exactly these curves. You get exactly these curves without bringing in the dropout information. But the percentages are quite different. You get a much lower percentage of those who respond to the drug, much higher percentage of those who don't respond, and a misestimated swing class, U-shaped class. Only 3% fall into this class in the MAR approach, which means that you probably wonder, is that class real or not? Is it trustworthy? But in this analysis, you get 18%, and it would then lead you to take a close look at the data, and indeed, there are observed trajectory patterns of this type in the data. So it's an interesting way of taking a closer look at longitudinal data that is a good segue to the mixture modeling that we're going to talk about in August, particularly the growth mixture modeling. So you have that paper. It is advanced stuff, but it belongs in this topic. Final switch then from the maximum likelihood analysis we talked about to Bayesian analysis. Again, multiply imputed data is an input data alternative in Mplus, and we can do this aggregation of estimates and standard errors and model testing as well. I have word now from Scott that we can stay here. The tech people will leave right in this time. We can have our question and answer session, and I can even stay a little bit longer with some of you if you want until 5:15. And they prefer, as Scott says, stay in this room, not spilling out there and talking. And again, you have to be quiet because guess what? There's an event.
Wine and cheese party.
Wine and cheese. But let me just say before I take questions, so here are all those neat references. Here is the longitudinal data handbook, longitudinal analysis, Fitzmaurice, Davidian, Verbeek, and Molenberg's. Here are the missing data references that I'm talking about. A good paper on pattern mixture modeling by Don Hedeker and Jennifer Rose, Natural History of Smoking. The classical book by Little and Rubin. Little's most recent overview of selection and pattern mixture model in that same longitudinal data book. And let's see, what else do we have here? Let's see, here's the Roy paper that I referred to. A sleeper, I think is a little overlooked. I think it's a great one. Here is a good psychological methods overview paper that I referred to by Joe Schaefer and Graham. Here is Joe Schaefer's book on missing data, mainly dealing with Bayesian and multiple imputation techniques. It's for the technical readers in this group. And that, folks, brings us to the end of the day and the reference section. So, with that, let's take some questions, if you have the energy. Yes?
I can't get beyond something, so maybe you can help. It's the Big Old Kenworth
Which slide number is that?
Slide 208 is the picture. And where does the information come from to estimate the regression of, say, D1 on Y1 or D2 on Y2?
Okay, so the question is about regressing D1 on Y1 here. So let me put this up on this side also. Yeah, so it's this regression. For people who drop out here, you have an imputed value here, in a sense. You know, you have a missing value that is in the maximum likelihood estimation is filled in by the EM algorithm. It's missing, but you use that Y star value to predict. That's why you have to do that numerical integration, because it is actually a latent variable predicting a categorical.
And it's imputed using the information that's from the estimates of I and S and Q.
Yeah, and the other observed information, which is the previous Ys. Okay. Yeah, it's very intricate. Yes.
On the mixture modeling and the selection, I noticed maybe it's because of what you just said. Ys from Y1 on are latent. Before, you've only had on the intercepts the only thing that's connected is YO. Here, the slopes and quadratic also have an arrow to YO. They never have before.
Right. I just drew it generally here. Even though you have paths from S to YO, some of those paths can be, or zero, would be zero in this application. Yes? 175. Yeah, so X bar refers to the listwise present group, those who have complete data. So let me just show 174 perhaps. So X bar and SX, X bar down here and SXX are using these people.
Just the top square.
Hmm?
Just that top square.
Yeah, right. Those who you would get if you did listwise deletion, right? More questions? You are tough. You don't look tired, folks.
Yeah.
All right. Well, maybe we have something there. Okay.
I don't know what slide to refer it, but you did mention the problem with low coverage. If you detect that you do have this problem, how do you deal with that, or are there any ways to deal with that?
So the question is about low coverage, and I would understand if the videotaping dies down at any moment. I don't know if anybody's there. That's all right. Low coverage, what do you do about it? Well, one thing you could do is skip the H1 estimation. You have a no chi-square option, for instance. Chi-square, to compute chi-square, you have to compute your H0 model and your H1 alternative fully unrestricted model. And it's the H1 model that is problematic when you have low coverage. For instance, if this said 0.05 here, that EM algorithm to compute that the corresponding covariance is going to stop. This is described in Joe Schaefer's book. So, but the H0 model may have no parameter. Your growth model may have no parameter that needs information from both m over 0 and m over 3. So it could do better. But generally speaking, you don't want to have low coverage, certainly not on the diagonal, because once again, then you compute your model estimates drawing too much on the model assumptions and too little on the information in the data. Yes?
You talked a good bit about some of the modeling of the missing data and how you could then test to see if you had violated MAR. Is that correct? Did I hear that right?
No.
No, I didn't think so.
That would be a no-no if I said that. No, you can test if you have MCAR. But the problem is you cannot test if you have MAR.
So what do you do if you're feeling at least...
If you feel uncomfortable?
In between what would be a MAR situation or an NMAR or MNAR situation?
What you do, if you're not, if you feel uncomfortable or question the MAR assumption, what you can do is a so-called sensitivity analysis, using a battery of selection and pattern mixture models to see if the results change very much related to, as compared to the MAR results. That's the only thing you could do.
You recommend doing a selection and
I would do that, yeah. Particularly since it's fairly easy. Yeah. Yes.
Can I go back to the selection model? Is there something in the code on page 209 that says to do that EM algorithm, or is that kind of lurking in the background?
It is, the default estimator here is maximum likelihood.
Yeah.
And in this case, it's a very peculiar case here. I'm glad you asked, so I can. Where are we? Selection modeling. Yeah, because we know that in maximum likelihood, when you have latent continuous variables, which this is when you have dropped out after y0, this is latent y star, you can think of it, and categorical observed, that leads to numerical integration. So it is a numerical integration algorithm that goes on in the EM setting. And the integration is a very peculiar one because the integration is not needed for those who don't drop out. So in algorithmic terms, the dimension of integration changes over people. And that then calls for the specific Monte Carlo integration technique used here. So this is quite intriguing algorithmic work behind the scenes there. More questions? And this is thanks to our our local algorithmic genius, Tihomir Asparoho. Yes?
Slide 39.
39? That's okay.
I'm just catching up.
That's good.
Besides that it's a different analytic question, is there a reason why we would want to use counts of police contacts chunked into intervals versus accumulated over repeated observations for a zip model?
No, I think use 2-year intervals to have a little higher counts.
Right.
Maybe there were too many zeros, too few non-zeros.
What if I wanted to know, like, the moving out of the zero class was an interesting question for me. Like,
Okay.
What predicts who gets out of?
Then you may want to stay with more fine-grained information. Yeah. Yeah.
In that same one, why did you eliminate one bigger than 10?
We were suspicious. There were relatively few, and we were suspicious that there was some kind of exaggeration going on. It was such an outlier behavior. Yes?
So the latent classes that you got under the four-class Roy model, you made a comment that with or without the dropout pattern, you ended up with the same latent classes but different percentages. Is that true in general, or is that true for this data set?
That's a good question. So to repeat it, in the Roy version of the pattern mixture modeling, we ended up with 4 dropout classes, reducing the 6 potential dropout patterns observed in the data to 4. And we found then that the 4 classes had this trajectory, and those trajectory shapes were the same as when we did not use the Ds. If I put my arm over these Ds, what you have here is your growth mixture model, latent class variable C, and only analyzing the Y information. And the question was, we did see the same growth curve shapes by different percentages. Should that always be expected? And I won't say, I don't know now. I don't think one can expect that But I think that says that in this application, it really is the different antidepressant reactions that drive the classes in Roy. In other applications, the classes may be more related to the Ds. And that's why, to disentangle those two, I suggest in this paper an extended Roy model where you have one C that's related to the dropout and another C that's related to the Y, to the antidepressant development. And that C for Y is not related to the dropout. And that model fits better. It has lower BIC than this model and gives, again, slightly different percentages and seem to be the more believable model when you bring in that distal outcome information on the 3 reasons for leaving phase 1 of the study. Yes?
Judging from your paper and this discussion, and I know you're speaking more on the next trip here, is this kind of modeling going to be more used in the future, particularly for longitudinal data?
The question is this modeling going to be used more in the future? Well, I think this modeling is a prime example of why we wanted to do Mplus. That is, bits and pieces of these models have been presented in the literature. I did some extensions, but it's been in the literature. Bits and pieces of statistical software written in fairly inaccessible programs exist. But since it wasn't put into a general framework, easily accessible, and easily going between the different models, I don't think sensitivity analysis of this kind has become standard. Maybe it will happen now. Or maybe people will say, this is too complicated, I'll just do MAR. We'll see. But there's a chance now that it could be expanded use of this.